Picture an ordinary Tuesday morning. You open your phone, check the weather, and see a small gray cloud icon. Light rain, nothing more. You leave the umbrella by the door and head out. By early afternoon, the sky has turned the color of a bruise, storm drains are overflowing, and a river is running down the middle of a street that has never flooded before. Somewhere, a meteorologist is staring at a screen, trying to explain how a forecast built on satellites, artificial intelligence, and some of the fastest computers ever built managed to miss this by such a wide margin. This is not a story about one bad forecast. It is the beginning of a much bigger question, one that scientists have been chasing for more than 60 years. Is it even possible to predict something as vast, as violent, and as strangely alive as the atmosphere of an entire planet? Scenes like this repeat themselves on every continent with unsettling regularity. A well-behaved low-pressure system, tracked by a global model and refined by a 50-member ensemble running on a machine that consumes as much electricity as a small town, is supposed to slide harmlessly past a coastline. 3 days out, the projected track can still wander by 100 kilometers or more. And for a city sitting right at the edge of that uncertainty, the difference between a light shower advisory and a flash flood emergency. It is tempting to hunt for someone to blame. Outdated hardware, missing data, human error at the forecast desk. But the deeper you go into how the atmosphere actually behaves, the clearer it becomes that the problem is not a broken part of the machine. The problem is baked into the nature of the system itself. We tend to think of weather prediction as a kind of arithmetic. Feed in the numbers, run the calculation, get the answer. But the atmosphere is not a spreadsheet. It is an ocean of gas, 30 kilometers deep, wrapped around a spinning rock, heated unevenly by a star 93 million miles away, sloshing over oceans, deserts, mountains, and ice sheets that all respond to that heat in completely different ways. Every second, trillions of parcels of air are exchanging energy, moisture, and momentum with their neighbors, in a system so tangled that no human mind, and arguably no computer ever built, can hold the whole of it at once. Understanding why weather sometimes refuses to be predicted means understanding what kind of machine we are actually dealing with. And it turns out to be a stranger machine than most people realize. Part of that strangeness comes from the sheer range of scales the atmosphere operates on simultaneously, and the fact that none of those scales stay politely separated from each other. At the largest end sit planetary waves, gentle undulations in the flow that stretch across thousands of kilometers, and can decide whether an entire continent runs warmer or colder than average for weeks. At the smallest end sits the turbulence inside a single cloud, eddies just a few meters across that decide whether rain falls on one street or the street next to it. In between lies an entire ladder of intermediate scales, cyclones 1,000 kilometers wide, clusters of thunderstorms 100 kilometers across, individual storm cells only a few kilometers in size. The defining feature of a system built this way is that the small scales do not stay small. A single thunderstorm a forecasting model fails to properly capture today can, through a chain of interactions, nudge the track of a much larger storm system days later. It is this constant crosstalk between scales, small feeding large and large shaping small, rather than any simple shortage of data, that makes the atmosphere such a formidable target for prediction. To see why, We need to travel back to a cramped office in the early 1960s, where a mathematician was running one of the first computerized weather simulations in history. He wanted to rerun a sequence he had already produced the day before. So he typed in the same starting numbers from his printout, hit go, and walked off to get coffee. When he came back, the new run bore almost no resemblance to the old one. At first, he suspected a broken vacuum tube or a wiring fault. What he eventually discovered was far stranger and far more important. The printout had rounded his numbers to 3 decimal places instead of 6, a difference smaller than the wobble of your hand holding a pencil. That tiny rounding error should have produced a tiny difference in the outcome. Instead, within a simulated month, the 2 weather patterns had nothing in common at all. The small mistake had not stayed small. It had grown, doubling and doubling again until it swallowed the entire forecast. That discovery became one of the 20th century's great scientific turning points, and it gave the world an image that has outlived the equations behind it. The idea that the flap of a butterfly's wings in one part of the world could, in theory, set off a tornado somewhere else weeks later. Most people who repeat that phrase misunderstand what it actually means. It is not a claim about butterflies causing storms. It is a precise statement about a class of systems that scientists call chaotic. Systems that are completely governed by deterministic physical laws, with no randomness or magic involved, and yet whose future is fundamentally unknowable beyond a certain horizon, because any uncertainty in the starting conditions, no matter how microscopic, grows explosively over time. The atmosphere, it turns out, belongs squarely in this category. Not because our instruments are flawed, not because our models are unfinished, but because of the very physics that makes weather possible in the first place. Here is a simple way to feel this effect in your own hands. No supercomputer required. Take a double pendulum, 2 rigid arms joined by a hinge, and release it from a certain angle. Then release it again from an angle so close to the first that no human eye could detect the difference. Within a handful of swings, the 2 pendulums will be moving in completely unrelated patterns, as if they had never shared a starting point at all. Multiply that single hinge by billions of interacting parcels of air, each one nudging its neighbors, each one sensitive to microscopic differences in temperature and moisture, and you begin to sense the scale of the challenge facing anyone who tries to predict the sky more than a couple of weeks out. The atmosphere is not broken. It is simply the kind of system where perfect knowledge of tomorrow requires perfect knowledge of today, down to a level of precision that nature itself does not permit us to measure. So where exactly does the forecast run out of road? Decades of research now point to a horizon of roughly 10 to 14 days. Within that window, a forecast still carries real, usable information, even if the fine details drift. Beyond it, the accumulated uncertainty grows so large that a prediction becomes statistically indistinguishable from simply knowing the season and the location. This limit is not uniform across the planet or across every kind of weather. Large, slow-moving features, such as a continent-sized zone of high pressure, tend to stay predictable for longer because their sheer size and inertia make them harder to knock off course. Small, fast, local phenomena, especially rainfall, lose their predictability far more quickly, sometimes within a single day. There is also a geography to this limit that rarely makes it into casual conversation about the weather. In the tropics, where temperature contrasts between neighboring air masses are weak, and much of the day's weather is driven by local convection, rather than large, sweeping systems. The useful forecasting horizon is naturally shorter, and a forecaster working in a tropical city may see tomorrow's outlook shift meaningfully within a matter of hours. In the mid-latitudes, by contrast, the large cyclones and anticyclones that dominate the weather are more inertial, more stable structures, easier to track and extrapolate several days ahead. Predictability, in other words, is not evenly distributed across the globe. A forecast considered reliable in one hemisphere might be barely useful a few thousand kilometers closer to the equator, simply because the underlying physics of the atmosphere behaves differently there. The reason for that gap traces back to something as simple and as familiar as a cloud. Water vapor is arguably the single largest source of unpredictability hiding inside the atmosphere. When moist air rises and its vapor condenses into droplets, it releases what scientists call latent heat, energy that was absorbed earlier during evaporation and is now given back all at once. That burst of heat strengthens the very updraft that produced it, in a feedback loop that can turn a fairly ordinary patch of humid air into a violent thunderstorm within an hour. A tiny error in how much moisture a model assumes at the start of a run, an error too small to matter for temperature or wind, can cascade through this feedback loop and produce a completely different storm just a few hours later. Researchers have actually tested this directly, building simplified versions of weather models with the moisture and convection physics stripped out. Without those processes, forecast errors grew roughly twice as slowly, stretching the useful horizon from 2 weeks to nearly 3. But you cannot remove clouds from the real sky. They remain baked into the system, and with them, an irreducible core of uncertainty that no amount of computing power alone can dissolve. This is exactly why a single thunderstorm remains one of the hardest things in meteorology to pin down in advance, even with every modern advantage available. A powerful storm cell can spin up, mature, and dump a month's worth of rain over a single neighborhood within an hour, all inside an area smaller than most global model grid cells, which are typically several kilometers on a side. For a model to genuinely resolve an individual storm, rather than just gesture vaguely in its direction, it needs an extraordinarily fine grid, and fine grids come with computational costs that scale up brutally fast. This is why, in that critical short window from a few hours to about a day ahead, forecasters lean less on global models and more on specialized, high-resolution regional simulations, paired with live radar tracking that can watch a storm cell being born in real time, rather than trying to predict its birthdays in advance. If a single perfect forecast is off the table, meteorology found a clever workaround. Stop trying to predict one future and instead predict many. This approach, called ensemble forecasting, runs the same model dozens of times, each time nudging the starting conditions by an amount smaller than any instrument could actually detect, well within the margin of measurement error. If every version of the simulation converges on a similar outcome, forecasters can speak with real confidence. If the runs scatter wildly, some showing sunshine and others a flood, that spread is itself valuable information. It tells meteorologists the atmosphere is currently sitting in a knife-edge state, one where the outcome is genuinely up for grabs. It is worth pausing on how strange this is. A weather forecast is not really a prediction of what will happen. It is a map of everything that plausibly could happen, weighted by likelihood. Most of the public never sees that map. They see a single icon on a phone screen, and when reality lands in the unlucky 30% of outcomes rather than the likely 70%, they call the forecast wrong, even though nothing about the science actually failed. This mismatch between how the atmosphere actually works and how humans prefer to receive information may be one of the most underrated obstacles in all of meteorology. People do not naturally think in probabilities. We want a yes or a no, a single confident answer we can plan a wedding or a hiking trip around. But an honest forecast is by its very nature a spread of possibilities. And every time that spread gets compressed into a single icon or a single number for the sake of a clean interface, some of the most important information, how confident the forecast actually is, quietly disappears. A 70% chance of rain that fails to materialize is not a broken forecast. It is one of the 3 times out of 10 when the less likely branch of the future happened to come true. Bridging that gap, teaching an audience to read uncertainty the way scientists do, may end up mattering as much for public trust in forecasting as any future improvement in the models themselves. None of this would be computationally possible without one of the most underappreciated engineering feats of the modern era: the numerical weather model itself. The idea is almost a century old. In the years following the First World War, a British scientist named Lewis Fry Richardson attempted to calculate a 6-hour weather forecast by hand, solving the fluid dynamics equations of the atmosphere with pencil, paper, and a small army of human calculators. The project took him months, and the final answer was wildly wrong, thrown off by tiny inconsistencies in his starting data that, decades before anyone understood chaos theory, were already doing their damage. And yet Richardson also left behind a startlingly prophetic vision, a fantastical image of a great circular hall filled with 64,000 human computers, each one calculating the weather for a different patch of the globe in perfect synchrony. Conducted from a central podium like an orchestra, he had, without knowing it, sketched a blueprint for the supercomputer 3 decades before the first electronic one was ever switched on. When those machines finally arrived in the 1950s, Richardson's impossible dream became a working reality, and numerical weather prediction was born. Feeding those machines requires an extraordinary amount of raw material, gathered from a global observation network that never sleeps. Weather satellites in geostationary orbit hover above a fixed point on the equator, watching entire hemispheres continuously, while others in polar orbit sweep pole to pole, scanning fresh strips of the planet every few hours, and profiling temperature and humidity through the depth of the atmosphere. Weather balloons launch twice a day from hundreds of stations worldwide, carrying instrument packages more than 30 kilometers upward before they burst. Ocean buoys track sea surface temperature. Aircraft log conditions at cruising altitude on nearly every commercial flight, and ground stations report pressure, wind, and rainfall by the minute. 2 tools deserve special mention. Weather radar networks reveal the internal structure of a storm in real time, spotting the rotating column of air inside a supercell minutes before it can produce a tornado. And specialized research aircraft, known as hurricane hunters, fly directly into the eye wall of a developing tropical cyclone, dropping instrument packages through the most violent air on the planet to measure exactly what no satellite can see from space. All of this information is stitched together through a process called data assimilation, a mathematical technique that blends fresh observations with the previous forecast to produce the best possible estimate of the atmosphere's current state. Any error introduced here, a mist balloon, a noisy satellite signal, a data gap over open ocean, becomes the seed that chaotic dynamics will later amplify into a much larger error days down the line. The scale of this observing effort is easy to underestimate. On a typical day, hundreds of thousands of individual measurements pour into forecasting centers from every corner of the globe, and a significant fraction of the planet, especially remote ocean and polar regions, remains chronically under-observed compared with densely instrumented continents. That uneven coverage matters enormously, because chaos theory guarantees that even a small blind spot, a patch of ocean where no ship, buoy, or balloon happened to be sampling at the critical moment, can seed an error that a model will happily amplify over the following week. It is one of the quieter ironies of modern forecasting that a storm brewing over a remote stretch of open ocean, far from any shipping lane, can sometimes be harder to forecast accurately than a storm forming directly over a densely populated coastline bristling with instruments. Beneath all of this atmospheric drama sits a second engine, one that moves far more slowly but stores far more power: the ocean. Water can absorb an enormous amount of heat before its temperature rises even slightly, thousands of times more than an equivalent volume of air, which makes the ocean the planet's single largest reservoir of thermal energy. Currents move that heat across entire ocean basins, from the equator toward the poles and back again, in a slow global circulation that regulates the climate of continents thousands of kilometers from the nearest coastline. When part of that ocean grows even 1 or 2 degrees warmer than usual, an event now known as a marine heat wave, it does not stay a quiet, isolated anomaly. Warmer water means more evaporation, more energy transferred upward into the air above it, and more fuel available for whatever storm happens to pass overhead. Recent years have brought record-breaking ocean temperatures in multiple basins simultaneously, and the atmosphere has been quick to notice. Far beneath the surface, on timescales that dwarf any single forecast, a much slower current is also at work. A planet-spanning deep ocean circulation, sometimes called the global conveyor belt, where cold, salty water sinks near the poles and pulls surface water in behind it, driving a loop that can take centuries to complete a single circuit. This is a useful reminder that the ocean does not forget the way the atmosphere does. A pulse of heat or a shift in salinity can echo through the climate system for generations, long after the atmospheric weather that first produced it has been forgotten by everyone except the water itself. It also explains a peculiar asymmetry at the heart of climate science. Models built to predict tomorrow's weather and models built to project the climate decades from now are, in a real sense, describing 2 different clocks running at 2 entirely different speeds, one ticking in hours, the other in centuries. Yet both are ultimately part of the same coupled ocean-atmosphere machine. One of the clearest demonstrations of the ocean's grip on global weather plays out every few years in the tropical Pacific, in a cycle known by 2 names, El Niño and La Niña. Periodically, sea surface temperatures across the central and eastern tropical Pacific swing well above or well below normal, and the exact trigger for this swing remains an active area of research, one of the genuine open questions in this field. But the consequences are extraordinarily well documented. The shift relocates the zone of intense tropical thunderstorms that normally sits over the western Pacific, And that relocation sends ripples outward through the jet stream in a chain reaction climate scientists call a teleconnection, ultimately reshaping rainfall and temperature patterns on almost every continent. A warm El Niño phase tends to bring drought to Australia and Indonesia, wetter winters to the southern United States, and altered hurricane activity in the Atlantic. A cool La Niña phase tends to push those patterns in the opposite direction. What makes this cycle so remarkable is the timescale involved. A 5-day forecast for a specific city can sometimes be harder to nail down than the broad seasonal tendency for an entire region 3 months out, because that seasonal signal is coming not from the chaotic atmosphere, but from the far more patient ocean underneath it. Weather and climate, it turns out, are not the same kind of prediction problem at all. High above the ocean's influence, in the upper atmosphere roughly 10 kilometers up, where commercial jets cruise, a narrow ribbon of extraordinarily fast-moving air circles the planet, the jet stream. It forms because of the sharp temperature contrast between frigid polar air and warmer air from the tropics, a contrast that acts like a pressure gradient, squeezing the wind into a fast, narrow channel, sometimes exceeding 300 kilometers an hour. Each hemisphere actually hosts more than one of these ribbons, a stronger, more erratic polar jet closer to the mid-latitudes, and a steadier, weaker subtropical jet tied to the broader tropical circulation. The jet stream acts as the great conveyor belt for weather systems, steering storms and clear spells from west to east across entire continents. When it runs in a relatively straight line, weather changes in an orderly, predictable rhythm. But the jet stream does not always run straight. It bends, sometimes into deep, looping curves, ridges of warm air stretched poleward, and troughs of cold air plunging toward the equator. And those bends can lock into place for days or even weeks at a time. That locking phenomenon has its own name: blocking. Picture a dome of high pressure that should, by all normal rules, keep drifting eastward with the rest of the flow, but instead simply stops, sitting in place like a boulder in the middle of a river, forcing every other weather system to detour around it. Blocking patterns are the hidden engine behind many of the most punishing, headline-making weather events on record. Heat waves that refuse to break for a week or more, droughts that stretch across an entire growing season, or the mirror image outcome on the other side of the block, where storm after storm gets funneled along the same detour route, dumping rain on the same unlucky region again and again. Inside a blocking dome, air sinking from higher altitudes compresses and warms simply through the physics of descending air, adding extra heat on top of whatever the sun is already providing, which is part of why blocked heat waves can become so extreme so quickly. Forecasting models have become reasonably good at spotting when a block is about to form. They remain far worse at predicting exactly when it will finally break down. And that single uncertain variable, the lifespan of a stuck weather pattern, remains one of the most stubborn open problems in medium-range forecasting. Some of the most punishing heat waves on record trace directly back to this kind of stubborn, stuck pattern, rather than to any single hot day. A dome of high pressure that refuses to move for a week or two does more than simply block cooler air from arriving. The air trapped underneath it is also compressing and warming on its own, purely through the physics of descending air, adding an extra layer of heat on top of whatever the sun alone would have delivered. And a block rarely affects only the region sitting directly beneath it. Somewhere nearby, storm systems that would normally have moved on are instead being funneled, one after another, along the same detour route, so that the same blocking pattern responsible for a suffocating heat wave in one place can simultaneously be dumping flood-level rainfall on a neighboring region caught in its wake. Bent jet streams create another phenomenon that has become impossible to ignore in recent years: atmospheric rivers. Long, narrow filaments of concentrated water vapor stretching thousands of kilometers from the tropics toward the mid-latitudes, carrying more liquid water by some estimates than the flow of the Amazon River itself. When one of these airborne rivers slams into a mountain range along a coastline, the forced upward lift squeezes out extraordinarily intense, concentrated rainfall. For coastal regions of Western North America and Western Europe, atmospheric rivers deliver a large share of the annual water supply, replenishing reservoirs and mountain snowpack that entire cities depend on. But the same structure that brings life-giving rain in a mild season can, if it strengthens or lingers too long, produce catastrophic flooding and landslides within days. Forecasters have started ranking these events on an intensity scale not unlike the one used for hurricanes, precisely because the difference between a beneficial soaking and a disaster is measured in a matter of degree, not kind. And because the river itself may be only a few hundred kilometers wide, a shift in its track of just that same distance can mean the difference between a valley receiving its entire winter's water supply and receiving almost nothing at all, while the valley next door drowns. Climb even higher into the stratosphere above the North Pole, and you find a third major player in this story: the polar vortex, a vast spinning pool of frigid air that forms every winter roughly 30 to 50 kilometers up. In its normal state, the vortex behaves like a wall, sealing the coldest air of the year up near the pole and keeping it from spilling southward. But occasionally, through a complex chain of wave energy rising up from storms in the layer below, the vortex weakens dramatically or even splits apart in an event called sudden stratospheric warming, during which stratospheric temperatures can leap by several tens of degrees within a matter of days. A weakened vortex loses its grip on the polar air pooled beneath it, and that air comes spilling southward into the mid-latitudes, sometimes producing cold outbreaks severe enough to break decades-old temperature records and strain power grids never designed for that kind of demand. The surface effects of a stratospheric disruption do not appear immediately. They typically take 1 to 4 weeks to filter down, which gives forecasters a genuinely rare gift: a heads-up window, extending beyond the usual 2-week predictability wall, warning that a bout of extreme cold is significantly more likely somewhere in the weeks ahead, even if the exact location and timing remain uncertain. All of this raises an obvious question, one that sits at the center of some of the most contested research happening in climate science today. Is the Arctic itself changing the rules of the game? The Arctic is warming faster than almost any other region on the planet, a well-established fact, driven substantially by the loss of reflective sea ice, which is steadily replaced by darker, open ocean that absorbs far more solar energy, accelerating the warming even further in a feedback loop scientists call Arctic amplification. Where the science becomes genuinely contested is what happens next. One influential hypothesis, first proposed over a decade ago, argues that shrinking the temperature contrast between the Arctic and the mid-latitudes weakens the jet stream, making it slower, wavier, and more prone to the kind of persistent blocking patterns responsible for extreme weather further south. This idea has spread widely in popular explanations of unusual weather. But a significant portion of the climate science community remains unconvinced, or at least cautious. Different modeling studies, using different methods and different time periods, produce genuinely conflicting results. Some find a real, measurable weakening trend in the jet stream. Others find no statistically significant signal once natural year-to-year variability is properly accounted for. This is not a sign that science has failed to do its job. It is what science looks like while it is still working. The honest answer at this point in time is that the connection is physically plausible, actively studied by serious researchers on every side of the debate, and not yet a settled fact. Down in the tropics, a different and increasingly urgent kind of unpredictability has been drawing attention. Storms that intensify explosively, sometimes transforming from a modest tropical disturbance into a major hurricane within 24 hours. This process, called rapid intensification, depends on more than warm ocean water alone. It also depends heavily on wind shear, the difference in wind speed and direction between the lower and upper atmosphere. Weak shear lets a developing storm build a tight, symmetric structure that efficiently converts ocean heat into rotational energy, allowing it to strengthen almost unchecked. Strong shear tears the top off a storm before it can properly organize. This is why the very same patch of unusually warm ocean can produce a quiet hurricane season one year and a run of explosive, record-breaking storms the next. The deciding factor is often not the water at all, but the wind blowing far above it. Storms add another layer of complication through eye-wall replacement cycles, in which a new outer ring of intense thunderstorms forms around an already mature hurricane and gradually chokes off the original eye wall, sometimes causing a brief dip in intensity before the storm reorganizes and reaches an even higher peak. Predicting the exact timing of that cycle remains one of the hardest problems in tropical meteorology, because it plays out on a scale of just a few kilometers. Precisely the scale that global models still struggle to resolve. And the practical stakes could not be higher. Rapid intensification can shrink the window coastal communities have to prepare or evacuate from days down to hours. Faced with a hard physical ceiling on predictability, meteorology has recently found itself in the middle of a genuine revolution. And this one has nothing to do with faster versions of the same old equations. Over the past several years, a new generation of forecasting systems built on machine learning has emerged, and the approach is almost the philosophical opposite of the traditional method. Instead of explicitly coding the equations of fluid dynamics, these systems are trained on decades of historical weather archives and left to discover, on their own, the statistical relationships that link today's atmosphere to tomorrow's. Early results stunned the meteorological community. One widely cited system, built by a major technology research lab, was shown to outperform the world's leading physics-based forecast on the overwhelming majority of verification benchmarks. And it could generate a 10-day global forecast in under a minute on a single specialized chip, a calculation that traditionally required hours of runtime on a machine room full of supercomputers. By early 2025, Europe's leading medium-range forecasting center had moved its own machine learning model into full operational status, running it side by side with the physics-based model the center had spent decades refining. It would be premature, though, to declare that artificial intelligence has simply solved the problem of chaos. These new models carry their own distinct weaknesses. They tend to underperform on rare, extreme events, precisely because such events are, by definition, underrepresented in the historical data used to train them. They have a documented tendency to smooth out sharp rainfall peaks while overproducing light, drizzly precipitation, a quirk researchers have started calling the drizzle problem. They still depend on traditional physics-based models to supply their starting conditions, and crucially, because they are trained to imitate the same chaotic physical system, they inherit the very same predictability ceiling their predecessors ran into, rather than somehow escaping it. There is also a subtler issue. Unlike a physics-based model, which is mathematically constrained to conserve energy, mass, and momentum, a purely statistical model has no built-in obligation to respect those laws and can occasionally produce outputs that quietly violate them, like a burst of negative rainfall in a spot where physically none should exist. Engineers working on these systems are already responding to that gap, building physical constraints directly into the architecture of the newest models, effectively forcing the statistics to respect the same conservation laws that classical equations enforce automatically. It is a genuinely active area of experimentation, with new model versions arriving every few months, and older ones, including some of the very systems that first proved machine learning could compete with physics-based forecasting, already being described by researchers as first generation and increasingly outdated only a few years after their debut. That pace of change is itself remarkable for a field that spent most of the 20th century improving in small, incremental steps. The most promising path forward, according to many researchers working at the intersection of the two approaches, is not choosing one over the other, but building hybrid systems that combine the physical guarantees of traditional equations with the speed and pattern recognition power of machine learning. There is also genuine momentum toward pushing these methods into forecasting's hardest remaining frontier, the awkward middle ground between 2 weeks and 3 months, sometimes called the subseasonal to seasonal gap, where slower-moving components of the climate system, ocean heat, soil moisture, snow cover, may offer a foothold of predictability even after the atmosphere itself has become genuinely chaotic and unknowable in its details. That awkward middle stretch, too long for a detailed daily forecast and too short for a broad seasonal outlook, happens to be exactly the window that matters most for farmers planning irrigation, utilities managing power demand, and emergency planners trying to position resources ahead of a difficult stretch of weather. Researchers chasing progress here have increasingly turned their attention away from the atmosphere itself and toward its slower, more patient neighbors. The moisture locked in soil, the extent of mountain snowpack, the persistence of a marine heat wave. None of these evolve fast enough to be affected by the same chaotic sensitivity that dooms detailed forecasts beyond 2 weeks, which means they can sometimes offer a genuine edge, a way of saying that a coming month is more likely than not to run wetter or drier than average, even when nobody can say with any confidence whether next Tuesday specifically will bring rain. It is worth pausing here to draw an honest line between what this story has established as fact and what remains open. Firmly established, the atmosphere is a chaotic system, sensitive to its starting conditions, and that sensitivity imposes a real physical ceiling on detailed forecasting, somewhere around 10 to 14 days, regardless of how much computing power humanity throws at the problem in the future. Firmly established, warmer air holds more moisture, and warmer oceans supply more energy to storms, direct consequences of basic thermodynamics confirmed by decades of measurement. Firmly established. Satellites, ensemble forecasting, and the relentless growth of computing power have transformed forecast accuracy over the past 50 years, turning what was once a same-day guess into a reliably accurate 5 to 7 day outlook. Still genuinely open. The precise strength and mechanism by which Arctic warming reshapes the jet stream and mid-latitude blocking. Still genuinely open. How far machine learning can push the frontier of useful prediction before it, too, runs into the same wall of chaos. Still genuinely open. The exact trigger mechanisms behind the El Niño and La Niña cycle, despite decades of dedicated observation. And still open, perhaps the biggest question of all. Whether denser observation networks and smarter models will ever meaningfully push the fundamental predictability horizon beyond 2 weeks, or whether that horizon is an absolute mathematical boundary, baked into the nature of turbulent flow itself that no future technology will ever cross. Before landing the plane, it helps to zoom out and hold several of these threads in view at once, because in the real atmosphere, they never operate in isolation. On any given day, a blocking ridge might be locked over one ocean basin, while thousands of kilometers away, a tropical disturbance quietly begins the process of rapid intensification, fed by a marine heat wave that formed months earlier and has nothing directly to do with the block. Meanwhile, the stratosphere over the pole may still be settling down from a sudden warming event 3 weeks prior, its influence only now beginning to reach the surface, even as the tropical Pacific slowly tips toward another El Niño phase that will not fully reveal its consequences until the following winter. None of these processes waits politely for the others to finish. They overlap, interact, and compound on timescales ranging from hours to years, which is exactly why no single model, no single number, and no single headline can ever fully capture what the atmosphere is actually doing at any given moment. Real forecasting is not one prediction. It is a constantly updated synthesis of many partially independent, partially entangled predictions, layered on top of each other like transparent sheets, each one true to a different part of the story. Return for a moment to that person standing at the door with no umbrella, staring up at a sky that betrayed the forecast. It is tempting to read that moment as a failure of technology, a story about incompetent meteorologists or outdated equipment. The truth is both less dramatic and far more interesting. Humanity has built one of the most extraordinary observational and computational systems in its history, a living network of satellites, balloons, radars, buoys, aircraft, and supercomputers, continuously devouring unimaginable quantities of data just to glimpse a few days into the future of the sky above us. And that system works astonishingly well. So well that we have largely stopped noticing what a miracle a reliable 5-day forecast would have seemed to a meteorologist working in the middle of the 20th century, who would have counted himself lucky to trust tomorrow's outlook at all. A century ago, nobody made travel plans around a 5-day forecast, because no such forecast existed. The only warning of tomorrow's storm came from the color of the sunset and the behavior of birds. Today, advance hurricane warnings routinely give coastal populations days to evacuate before landfall, a capability that has saved countless lives compared with an era when a storm could arrive almost without notice. Consider for a moment how much of daily life now quietly depends on forecasts most people never think twice about. Farmers time planting and harvest around a rain outlook. Airlines reroute flights around a jet stream pattern spotted days in advance. Power grid operators shift generation ahead of a heat wave they can see building on an ensemble map a week out. Shipping companies plot ocean routes around storm tracks calculated on the other side of the planet. None of this infrastructure existed a century ago, and all of it now runs, largely invisibly, on exactly the same chaotic, hard-to-predict atmosphere this documentary has been describing. The imperfection of weather forecasting is not a footnote to an otherwise finished science. It is the central, defining fact that every one of these systems has been engineered around, a permanent feature of the problem, rather than a temporary bug waiting to be fixed. And yet the very same system runs headfirst into a boundary that was not built by engineers at all, but by the underlying mathematics of turbulence itself. A boundary beyond which accuracy simply dissolves, no matter how much additional data or computing power gets thrown at it. Perhaps that is the real lesson buried inside the history of weather prediction. Not that science has failed against the atmosphere, but that certain systems in nature are constructed in such a way that perfect predictability would actually contradict the physical laws that make them what they are. Earth's atmosphere is not a machine running on rails, executing a program written in advance. It is a living, restless, endlessly evolving system, one in which the past only partially determines the future, and in which our knowledge of the present moment quietly dissolves into its own complexity the further ahead we try to look. Every new generation of instruments, every new architecture of forecasting model, pushes the boundary of practical predictability a little further outward, reveals a little more detail hidden inside the chaos. But fully lifting the veil of uncertainty from tomorrow's sky, let alone the sky 3 weeks from now, will likely remain permanently out of reach. And the deeper scientists dig into the atmosphere, the clearer it becomes that every question they answer opens up another, subtler, more fascinating one behind it. Maybe that is exactly why the forecaster, a job most people picture as routine and unglamorous, spends every working day face to face with one of the most genuinely thrilling puzzles in all of physics, unfolding directly above our heads, whether we happen to be looking up or not.